Yeah, for those of you keeping track, we are on the ninth week of the semester already. It is flying by. We are almost 2/3 of the way, I guess, um, going through this. But October is kind of a long stretch. I get that. Been kind of a long time without a break. So I appreciate all your hard work. Keep it up as best as you can. The last homework that I just graded, well, first of all, I was in the middle of grading it when Canvas went down. And so half of you got your papers back like on Sunday, and the other half had to wait like 24 hours. It was down for a long time. I was right in the middle of grading, I think it was Jean's paper, when I wrote a comment and it didn't save. And I was like, oh, this is no big deal. I'll just reload it. And then I found out soon enough that I wasn't going to be able to put any more comments on anybody's papers for another 15 hours. So I had a bit of an interruption in the middle there. But I would say definitely take a look at my solutions. That last homework, we took an extra day on it, and I know why. It was because it took a lot to write it all out. And um, there were some very, very good papers, but there were also a few folks who might need to sort of just practice tightening it up a little bit, especially like the induction. You have to write it all out. Here's the base case. Here's the induction step. What I'm going to make it very clear. I'm going to assume this, and then here's what we need to show, which is usually the n-1 version and then the n version. If you don't write some of those words in there, then I see the equations kind of all mixed together, and I don't know what's being assumed and what's being shown, and it gets a little bit hard to follow. So just a suggestion on that, as much as I know it's hard to write all that stuff out all the time, to just keep working on that. Anyway, as far as this week goes, we do have just an assignment due at the end of the week. Did I say I was going to let you work on it till Friday? I think I did. And that's because I'm not going to be grading them on Thursday. I have another class that has an exam on Thursday. So I will be busy with that. And so you guys might as well take some extra time. But on Friday, I'm not sure how much I'll be around. If you have any last minute questions on Friday, I think email would be the best way. For catching me in person, I would try to do that after class today or anytime on Thursday. I will tell you that because of my exam on Thursday, there will probably be a mob scene of 250B students outside my office for that. So you may need to just be patient with me on that. But anyway, tonight I'll be around, and Thursday I can certainly help you as well. So feel free to ask some questions. We are going to finish what we're going to say about chapter 7 today. And then we are going to move into graph theory. So actually graph theory starts in, I believe it's chapter 11. So we are going to skip over, we're going to skip over chapters 8, 9, and 10, at least for now. I always like to leave the door open. Maybe we'll come back and have some time to look at some of those intervening topics. But we are going to switch gears completely. And I think you're going to like it. I think you're really going to like the graph theory. It's usually when I teach this class, people really, they really get psyched up with what we're going to say about graph theory. So we're going to be pursuing it from a very theoretical perspective, which is not normally what you get, right? In computer science, it's all about the algorithms and coding it and getting it to spit out answers for you in that sense. This is going to be much more the theoretical side of graph theory, which I think is really cool. But before we get to that, and that'll be for the next week's homework and the next several weeks' homework, we'll be having some graph theory. You'll notice that my solutions will switch from being PDFs to being DOCs because I've had to insert pictures into my solutions, and I use that. I don't do that so much with PDFs. So you'll notice that as we go along. But yeah, what I'd like to do today, guys, is finish up a little bit more on generating functions, just so you guys know. With this generating functions thing, we are just taking a glancing look at it. I am not like, this is not a major topic. I think last year when I gave the final for this class, I didn't even have it on there. It was just a passing thing, one assignment, just a small handful of problems. So don't worry too much that this is going to be a major theme, but I at least want you to have a little bit of at least a brief exposure to it. And so that's what this is about. Remember the basic idea here. I've kind of tried to put it back on the board again from where we left off the other day. We're taking sequences of numbers and we're just associating them with these infinite series, right? The coefficients of this infinite series are just the terms of the sequence, the numbers that are making up that sequence. And if it's a finite sequence, no problem. That just means that your series would be a finite series. Okay, so it's literally cutting and pasting the numbers from the sequence into the generating function. If I gave you the sequence, you could write down the function. If I gave you the function, you could write down the sequence. The only question really is whether you could get a closed form for the infinite series. So you see here, I've got these dots, right? So the question is there a way to represent this infinite series as a algebraic expression that is completely self-contained? Or are we forced? I mean, if it's just a random bag of numbers, right, you're probably not going to be able to simplify what you have as an infinite series in a nice way. But there are certain situations when you can, right? And we saw some of those last time. For example, one of the best examples is in the case, so these numbers here, this particular series, if we imagine fixing k. So take a specific number for k, that just your favorite number. Maybe just to start this off, we could imagine k equal to 1. If k is equal to 1, then you're looking at 1 over 1 minus x. And the coefficients here, if k is equal to 1, these coefficients are all just equal to 1 because you're choosing 0. Anything choose 0 is equal to 1. And so all you're doing here is you're adding up 1 plus x squared plus x cubed. The most famous infinite series of all, right? So this is one that is kind of blazoned into my brain, at least. It's just the most common infinite series that there is that you would have. And remember that we're not thinking here, guys, in this topic of generating functions, we're not thinking of plugging numbers in for x, right? A couple people have been asking me about this. We're not actually trying to evaluate these series, or we're not really even asking questions of convergence, right? That's an analysis topic. That's not really what combinatorics is so concerned with. These are just simply symbolic expressions, right? Where the powers of x are kind of serving as placeholders, actually. Like I could almost just, instead of drawing them out as a power series, I could almost just make slots. And the sequence values are just going into those slots, that's all. So try not to get too caught up in the weeds of, well, I wonder if this converges or not, or what values of x am I looking at? We're not really doing any of that, right? We're just viewing it as a algebraic expression. Anyway, so when k is equal to 1, we get this very famous formula. When k is equal to 2, we actually did that one on Thursday last week as well. When k is equal to 2, what you're actually going to generate here are just all of the positive integers. 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on, right? So if k is equal to 2, we could write this one down as well, just so we can explicitly see it. 1 over 1 minus x, if we square that, then according to this formula here, when k is equal to 2, we're just getting, what is it, n plus 1, choose 1, which is really just n plus 1, right? So you would have 1 plus 2x plus 3x squared plus 4x cubed and so on. And so there's another example of a generating function. I should put this in here, so this is totally visible, right? And so we actually made some of the connections between these by taking derivatives. And we said, oh, the derivative of 1 over 1 minus x is actually the square of 1 over 1 minus x. And if we take the derivative on the left side, term by term, we get exactly the series that you see on the left side here. So it's absolutely fair to bring in your calculus knowledge into this discussion as well. And we basically generalized this for any exponent k. And what we saw is that actually, if we want to find the sequence that is associated with 1 over 1 minus x to the k, it is actually the stars and bars sequence right here. I'm just reminding you guys that you have k minus 1 bars and you have n stars, which is something from a totally different part of our semester. The stars and bars technique for counting things. Turns out that we can put those coefficients into an infinite series and it turns into this nice closed form expression, 1/1 minus x to the power of k. And then I just tried to explain, look, actually, if you take the 1/1 minus x and you write it out k times here, and you start imagining foiling this out, you just imagine foiling this out, you're going to grab some x's from here, you're going to grab some x's from here, you're going to grab some x's from each term when you foil this out. And all you're looking for is, you know, how many ways are there to grab a total of n x's? So you grab some from here, some from here, some from here, and so on. And there'll be lots of ways to do that, but that's actually just solving this stars and bars problem right here on the bottom of my board, which is actually kind of cool, right? So it ties in nicely with something that we learned how to count solutions to quite a while ago as well. So I think that's kind of interesting. So far, so good. Any questions? This is just kind of reviewing where we left off on Thursday. I just wanted to remind you about this very important example that we had, and just the general idea here behind generating functions. Let's just maybe do another example. Let's just kind of get warmed up here for the new week. I'm going to come to this board and write out an example. So here is an example to practice what we've just kind of reviewed. I would like to, so what I'm gonna do right now, guys, I'm gonna give you a generating function. I'm gonna ask you what's the sequence that goes with it, okay? So the question is, for what sequence? Okay, let's just try to milk this correspondence a little bit. Let's see if we understand how this works. For what sequence is, I'm gonna call this g of x. And let me write it out for you. The first factor is going to be 1 plus x squared, up to x to the 6th. Actually, I want to write out all the terms if you don't mind. I'm sorry. 1 plus x squared plus x cubed plus x to the 4th plus x to the 5th and plus x to the 6th. Let's just write it all the way out. And then times x plus x squared plus x cubed. And then times 1 plus x squared plus x cubed. And this one is going to go ... forever. So something along those lines. For what sequence is that the generating function? What sequence is that actually the generating function? So in other words, we're trying to figure out, well, what is the coefficient of x to the n, right? Because the sequence values, these h sub n's, those are just the coefficients in front of x to the n. So in other words, just i.e., what is the coefficient of x to the n? This is really just boiling it down what our question is. If we know what that coefficient is, then we'll know what the sequence, the terms of the sequence are. Okay, well, the coefficient of x to the n is going to be for some fixed, so if I fix a value of n, I'm going to ask myself, how many ways are there to grab some of these x's, some of these x's, and some of these x's, so that we have a total of n of them. So when I think about this, just the way I recommend that we think about this is that we fix some, n greater than or equal to 0. Just in your mind, imagine that that is a fixed value. And we are looking for the coefficient of x to the n in this case. Okay, so that's just a logical way to think about it. And the way that we can think about this is we're looking for, I've already said it, I just want to write it into the notes now. We're looking for the number of solutions or the number of ways to get x to the, I'm going to call it E1 times x to the E2 times x to the E3 to equal x to the n. The E1, E2, and E3 are the exponents associated with each of these three terms. There's the three factors. I have three different parts or factors in my generating function, and this is what we want to get. In other words, i.e. E1 plus E2 plus E3 equals N. Because the exponents obviously have to match. Right? So everybody knows that basically when you multiply powers of X, you just add the exponents. Okay, but with this constraint now, so we actually have constraints in this case, specifically E1 cannot be more than 6. Right, so I would just lay it out this way, 0 is less than or equal to E1 is less than or equal to 6. And then E2, which is this exponent, has to be between 1 and 3. So 1 less than or equal to E1, less than or equal to 3. Right, and then I'm sorry, that's E2. Sorry, E2. So E2 is between 1 and 3. And then finally, the third exponent actually doesn't really have any constraint, it's just anything greater than or equal to 0. Like that. So this should remind you of basically solving a stars and bars problem, right? You're trying to solve this equation, but you have some constraints, some violations or constraints that we have to take into account. So let's see if we can get that all worked out. The way I explained this back in the day was, well, if there's any lower bounds on these E's, we just kind of subtract. It's like going into the store and grabbing the apples and taking them right back out again. So in this case, we do have a lower bound on the E2, so we would remove that immediately, which basically just takes away one of my stars, right? So it would just take away one of my stars. So what we would end up with is, so let's just say shifting variables. Just kind of review, this is kind of old stuff now. We basically have, E1 plus, I'll call it E2 prime plus E3 equals N minus 1, where E2 prime is just literally E2 minus 1. So you just do a little shift of that variable. We don't need to change the E1 or the E3 at all, but E2 prime is therefore between 0 and 2. Right, so we have a new constraint on our middle variable, but we've also removed one of our stars. This should be looking like what we did before, maybe not quite the same notation, but it's exactly the same process. Everybody with me? Yeah. Let me know if I'm going too fast, guys. I get excited. And I don't mean to do it, but sometimes it happens. So now what I'm going to do is just solve this with no constraints and then subtract violations. Right, it's my usual approach. So in this case, so without constraints, let's see, what do we have? We have this many stars. We have, how many bars am I going to use here?
2.
2 bars to separate my 3 variables, right? So stars plus bars, I'm going to just choose my bars. So without constraints, I think I'll just write it down. N minus 1 plus 2, choose 2 is what it would end up being. Okay. And then I have to think about my violations. Violations would be if any of my E's was too big. I actually only have 2 violations, which would be the E1 violation here or the E2 prime violation here. There is no limitations on the E3. Okay, so let's think about violations for the E1 variable. Remember how we do this? If it says, so if we want to violate this condition here, just to review, this would just be if E1 was greater than or equal to 7.
Yeah.
And so we would remove 7 stars from the problem. And so I'm just going to go ahead and subtract 7 stars right there from, this is for E1 greater than or equal to 7, right? So I'm just throwing that as one possible violation. But that's not the only one. The other violation would be for the E2 prime. In that case, for the E2 prime to be a violation, it would have to be greater than or equal to 3. All right, so let's remove 3 stars here. So this is N minus 1 plus 2 minus 3. And we're still choosing 2 bars. Every time it's going to be 2 bars. But we're really faced with inclusion exclusion here, right, on the violations, so we could have E1 too big, we could have E2 too big. We count both of those scenarios, but we have double counted cases when both of these were true. And that would be removing 10 stars from the problem, so let me add that here, n minus 1 plus 2 minus 10, choose 2. These are the violations. And so let's get our answer then. Pretty sure that this is going to be hard to see from that distance. Let me move my camera over here closer. Let's get our answer, which is where we're just going to take our total without, now I'm going to clean this up as I go. So like this first one, I'm going to write it as n plus 1, choose 2. And then I'm subtracting this, which is my violation. So let's see, what do I got here? This is n minus 6, choose 2. And I have to also subtract this one, which would be, what is it, n minus 2, choose 2. And then this one, it has a minus sign here, but remember we're subtracting from the total, so it actually gets added. It's a double negative on that. So I go back to plus, and I have plus n minus 9, choose 2. So that should be it. And this would be H sub n. That would be your sequence. That is actually the answer to this question. For what sequence is this g of x going to be my generating function? The answer is it would be for this sequence of numbers. Let's just check it out. What is H0? I just want to get a couple of these terms just to kind of get the hang of it. If I plug in 0 for n everywhere up here, how much do we end up with? Well, if we end up with negative numbers on top, we can't do, with those terms would be 0, right? I can't choose a negative number from a negative pool. So none of these things matter. When n is 0, I just get this. Oh, if n is 0, this just becomes 1, choose 2. What's that equal to? 0, right? You can't take one object and choose 2. So actually nothing is adding up in this case. Now, if you were to FOIL this out, what that says is there would be no constant term. There would be no constant term in your generating function. And you can see that that's the case because you've got, if you factored this thing, at least from this piece, you'd at least get one x coming out. There is no term without an x in it, right? What's H1? Just play with this for a second. H1, according to this formula, is 2 choose 2 minus a bunch of zeros. Well, 2 choose 2 is 1. Now, is that the correct answer? If I think about, if I FOILed this out and I ask, what is the coefficient of x? Just x, right? Well, how could I make only an x? I would have to pick this guy. I can't pick the x squared or the x cubed. I would have to pick this one, which means I would have to pick this one and this one. There was one way for me to do that. There was only one term in this FOILed out expansion that would just have an x on it, and so the coefficient is 1. Making some sense? Should I do one more? This is, I just like to test drive my formula. Let's make sure it's reasonable. What if n is 2? Well, again, we're actually only going to get this term. The rest of these terms are all going to be 0. So this is actually just 3 choose 2 minus nothing, 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 right? So it should just be 3. What that says is that there ought to be 3 ways to make x squared. And is that true? I can pick this x. And if I do that, if I pick this x right here, then I can either pick an x and a 1 or a 1 and an x on the outer 2 factors. Or my other choice is to pick this x squared, in which case I must pick the 1 here and the 1 here. That looks like 3 ways to do it. Okay. So this is really what's happening, guys, is we're figuring out, you know, the h sub n's are just the number of ways of solving this equation. It's the number of ways of getting the number of ways of getting x to the k power, or the n power, I should say, to show up in the FOILed out expansion. And it's very much tied in with the stars and bars. So it's kind of interesting. Just see if there was anything else I wanted to point out about that. Cited H2. Yeah, it's pretty good. Yeah, if you don't believe me, just try a few more of them. I have it in my notes, I wrote them all out, but I don't think I'm gonna do that right now. Let me give you one more example, something a little different. Are we good on this? Okay, let's try, I mentioned this last time, but I'm gonna give you another somewhat different example. Instead of asking you to give me a sequence based on a generating function, let's see if we can. Oh, you know what I forgot to do? And so I just erased it. So I had, this is something else that I maybe won't do it right now, but if you look at this expression that we just had, this is not closed form. Because again, I've got my dots going off here. So if you wanted, you could ask yourself whether you could simplify this. So if we add up the first 6 powers of x, there is a formula for that you can use for a finite geometric series. I think I wrote this down last week, right? So 1 plus x squared and so on up to x to the 6th could be written this way. This one, I could factor an x out of it, and then I would be left with 1 plus x squared, which we could then write as x cubed minus 1 over x minus 1. And then this one is just our good old 1 over 1 minus x. So this is now starting to look like a closed form formula for the generating function. So I just wanted to point out that algebraically, you can rewrite it in this fashion. Now you really can't simplify that well with this. I mean, you could, this x doesn't cancel with anything on the bottom, so you can't really combine anything together here. But just so you know, we can get a closed form formula for that function as well. Right. Okay, that was really all I was trying to say there. Let me, though, give you one more example here. Let's just do it right here. And then I think we'll just call this good for now. Let's find a generating function. So on the last problem, I gave you the generating function and asked you to find the sequence. Now I'm going to ask you to find the generating function based on a sequence. So find the generating function for the number of ways. Find the generating function for the number of ways to select n pieces of fruit. I'm going to go back to my fruit example earlier in the semester. The number of ways to select n pieces of fruit from apples, bananas, oranges, and cherries if we can take, so I know there's a lot of writing here, I'll slow down. The number of ways to take n pieces of fruit, and we're going to use apples, bananas, oranges, and cherries. If we can take, and now I'm going to give you 4 conditions, all 4 of these conditions. At most 4 apples. So we can take at most 4 apples. Secondly, we have to take at least 3 bananas. Thirdly, we would have to take an odd number. That's a weird one. An odd number of oranges. Okay, so you can take 1 orange, or you can take 3 or 5, but you can't take an even number. And then finally, for the cherries, it has to be a multiple of 5. A multiple of 5. At most 4 apples, at least 3 bananas, an odd number of oranges, and a multiple of 5 for the cherries. Okay. Kind of crazy. Maybe you have 5 people at home and everybody has to have the same number. I mean, come on, this is reasonable. Don't wanna start a fight. Okay. So, if we didn't have conditions C and D, we would have just solved this, in the usual way, adding the apples to the bananas, to the oranges, I'm just scribbling for right now, so you don't need to take any note. I just want to remind you, basically, you're saying I want n pieces of fruit. You've got apples, bananas, oranges, and cherries, and there would have been something about, okay, so x1 is at most 4, and x2 is at least 3. And so we've solved this kind of problem before, just by using stars and bars, handling these conditions, subtracting violations, all that good stuff. We know how to do this type of a problem. But the weird thing now would be, well, what if we now are forced to take an odd number of oranges? That is a different kind of condition, right? I mean, you might think, oh, I'll just subtract violations. Well, the violations would be to take an even number of oranges. Well, that doesn't sound any easier, right? That's just another problem of the same nature. Multiple of 5 of something, right? So the third and fourth conditions here is something we have not dealt with something like that before. So this is where the generating functions can actually be quite helpful. So let me basically tell you that we're going to write down a generating function for this we're not necessarily going to solve for all of its coefficients, but we're going to at least try to write down the generating function for this. So for the solution, right, when I'm thinking about the apples, I can have at most 4 of those, right? So would everybody agree that if I have at most 4 apples, that I would create a factor that consists of these options? So I can grab either no apples, 1 apple, 2 apples, 3 apples, or 4 apples. Any of those is okay, right? So this is for the apples. And then for the bananas, it says at least 3 bananas. Well, that's just going to start at x cubed, right? So that would be 3 bananas, or 4 bananas, or 5 bananas, or more and more and more. We can take larger and larger numbers here. So let's add that to our expression. So these are the bananas, at least 3 of them. What do you suppose is going to be the factor that addresses odd numbers of oranges? Was that? Yeah, just all the odd powers of x, right? So we'd get x and x cubed and x to the 5th and da 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 da, right? Like that. And then to deal with, so that's for the oranges. And then finally, for the cherries, it says a multiple of 5 cherries. Well, that could be no cherries, or 5 cherries, or 10 cherries. So these are just the powers of x that are actually multiples of 5. So 1 plus x to the 5th, plus x to the 10th, plus x to the 15th, and so on. This making sense? Actually, you may find this surprising. That's the whole answer. Like, we don't have to do anything else. If I'm looking for the coefficient of x to the n, right, that would mean that I'm trying to grab some of each of these fruits. I want a total of n pieces of fruit, and my constraints are built into these expressions. I don't have 5 or more apples. I don't have less than 3 bananas, right? I don't have even numbers of oranges. I'm forced to pick the correct. I'm forced to pick my fruits so that they satisfy the 4 conditions over here. You see what I mean? So this would be it. Now, if you want, again, this is not a closed form. So, but this is the answer. Now, I can rewrite it using a closed form, and I think I will, just to kind of show you again. This finite geometric series here, 1 plus x squared plus x cubed plus x to the 4th, that is just x to the 5th minus 1 over x minus 1. Yeah, was it?
Notation purposes, what was the formula for the finite conversion?
Oh, the finite series?
Yeah.
Yeah, we should probably write that down again. So this is just gonna look like this one, right? 1 plus x squared plus x cubed, dot, 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 up to, let's just say x to the k. right? So everybody needs to know this. It's just the next power of x up minus one all over x minus one. So I always tell people if they want to check this, you just take the denominator on this side and multiply it by the other side. You just cross multiply it and just make sure it works out. That is a good one to just kind of put in your mind because it does show up a fair amount. So that's the apples piece, kind of in a closed form. And then if I want to put the bananas in a closed form, I would need to factor, what I would do is I would factor out the x cubed from this. And then once I factor out the x cubed, you can see what else is there. I have a 1, an x squared, an x cubed. Well, that's just the 1 over 1 minus x. Okay, so we can put that in there as well. What about the oranges here? So these are the odd powers of x. What do you suppose I'm going to do with that? Factor out an x. I would definitely suggest that. After I factor out that x, then you see that what I'm left with are the even powers of x, and this is just an infinite geometric series as well, but instead of an x, now we have an x squared. So it's going to be 1 over 1 minus x squared this time. It's the same exact series, but just with x squared instead of x in it, right? And then by the same token, for this last factor, these are, again, terms of an infinite geometric series, and the ratio this time is x to the 5th. So I'm just going to add one more term, which is 1 over 1 minus x to the 5th, like that. So this is what you would actually have. Ooh, that's interesting. You might notice that x to the 5th minus 1 cancels with 1 minus x to the 5th. There's just a sign difference there. Actually, what might be better is if we come back here to this equation again, guys. You can obviously just flip the order of the subtraction on both the top and the bottom, and you're not messing with it at all. So I might recommend that. Can we make that change here? It will just look better. It's not wrong what I wrote before, but in terms of simplifying it, I think it's gonna look a lot nicer like so. Okay, so that's just rewriting this thing. And then where is my blue marker here? I'm just gonna cancel some stuff. So I've got a 1 minus x to the 5th, which cancels this 1 minus x to the 5th. And let's see what we're left with. I see 4 powers of x on top, because I have x cubed times x. And then what do I have on the bottom? Well, I have 1 minus x, and then I have 1 minus x again. And actually, 1 minus x squared can be factored as 1 minus x times 1 plus x. So I actually could write that as another factor of 1 minus x, and then times 1 plus x. So if you want a nice closed form formula for your generating function, that would be it. That would be it. So this would be, isn't it amazing? If you write this out as an infinite series, the coefficients of it are the number of ways of solving this fruit problem. Pretty remarkable coincidence, actually. Okay. So that's the generating function for that problem. But it would be fine to just, this first line is totally correct. It's just not closed form. I do think you should be able, in some cases, I mean, you're not always going to be able to simplify these, but when you can write down a closed form formula, it's always a bit nicer. It's always a bit nicer. So anyway, yeah, you know, that's most of the brunt of what I had on this. I don't know. The homework, one of the problems asks you to make up a story problem to like that match. They give you the generating function, so they give you this, and then they ask you make up a story that would have that generating function go with it. And so the story in this case would be, oh, you're going to the store and you're buying these kinds of fruits, and then this would be the function for it. So you can make up whatever story you want. It's not that crazy. I'll just put it that way. To do those kind of questions. Okay. Question. Oh, yes.
And one of the onward problems is a slight variation of the last example you did, where
Okay.
instead of E1 plus E2 plus E3, they have like coefficients that are not one. Is there, how do you handle it?
Oh, so it'd be like,
So it's like.
instead of,
2E1
instead of this equation here,
Yeah,
we'd have like two E1 and.
plus 5E2 and stuff like that.
Okay, so if you have that, okay, I'm just gonna scribble for a second. Let's suppose that you were looking for two E1 plus E2 plus E3 equals N or something like that, right? This is just saying that in terms of gathering up your N pieces of fruit, whenever you grab the apples, you must be grabbing them two at a time. So your generating function for that is going to be forced to take the higher powers of X. So this would be, oh, I either have no apples or 2 apples or 4 apples or 6 apples and so on. So that's the way you would interpret that. The rest of these would be just the same. Right? Does that make sense? Okay, so that's the way to kind of interpret that. Yeah. Okay, good question. Any other questions? So good. Did you guys all bring the group? Well, I actually have some extra copies. This group work that we started on Thursday last week had 5 problems on it. It's kind of a long group work. And I know that I didn't let everybody finish it. I think most groups did numbers 1 and 2 last time. I have extra copies of this, if anybody didn't bring one with them. Did somebody else need a copy right now? Yes, it's you. Yeah, it's okay, I got a lot of copies. Who else? Copy here. What I'm gonna recommend, what I'd like you guys to do with this, I'd like you to go back with your groups again and try problems 3 and 5. Okay, so everybody probably did number 1 and 2. I'm not worried about number 4 because everybody on the homework did great on those types of problems. But problem 3 and problem 5, I'm gonna give you guys 15 minutes or so to see what you can do with those as a group, and then I'll come around and give you a hand, okay? So why don't we turn ourselves loose on this, just wrap up the recurrence relations a little bit. Just, you know, if you do what you can, but I understand it's a little hard to stay focused.
Yeah. No, you turn up the volume.
I'm scared.
I mean, at that point.
So like that's not too bad. It's just not what it matters.
Mason, am I meeting with you tomorrow?
I see.
Okay.
It's soon.
I'll find out. You don't need to look at it. I'm sure it's on there. Sure it's on there. Alright, I'll let you guys work on, you're working on number 3?
Yes.
Alright, great.
So like they start with this. We have to be greater than.
I thought we did this.
How many ways are there to pay on your $1 one?
Yeah, if it is the one that's like, well, you have to start off knowing what I'm gonna do. I'm not expecting.
Let's have our.
Just all you guys need to do.
Too much.
If you want to solve it, for what route you have. Like, sure, yeah, that would take a minute. Yeah, that would take.
I was thinking about the symmetry argument.
It's hard to say. Like one,
We're supposed to have it, you know, like
two,
No.
we have like.
five.
Yeah, I know.
Five.
The group work isn't like some selector so much. This isn't.
Yeah,
really on
this is from, last.
Yeah, it's really more from the last week. We're just going back to the old.
And we're gonna have in classification.
Yeah.
We need to- Some of the most fun.
All the
Yeah, that's right.
coins, the bill fees.
It's the same thing we had last week.
So
It's just fair line.
Yeah, look at that.
Ian is the correct one to make money, right? So you already have $100. What is that to make? I don't know.
Just writing out.
Stuff. So how many $100 bills can you add, I guess, how many years? Yes. A little bit of overlap too. Adding 10 of these is equivalent. No, adding 5. I'm trying to think. Oh, okay, Bill, like, so there would be 2, when we have a 1 over. Instead of.
If you take your bill of N-1 peso,
Yeah.
then you can tack on a 1 peso coin at the
Or
end.
$1 bill.
Oh,
So $1. There's no $1.
There is no.
Oh, yeah.
Yeah, but I know what you mean. You stick whatever gets you to N-1 peso.
Yeah.
That's called.
And then how many ways do you have?
And then you add, you know, how many ways are you?
Like last time, the big screen, and then it's like, oh, are we starting with?
There's still only 1.
Right.
I got you.
Yeah, that's kind of the way you want to play
So
it.
which more bits are in?
Yeah.
So Louis,
I don't see.
And it'd be 5.
Is this the answer or the start of the?
This is us writing stuff down.
Okay, you're off to a good start. So if you paid N-1 pesos,
We can have.
then every one of those ways that you could have paid that, which is you said N-1, because you can now add on a 1 peso coin. And now you are at 5 pesos. So you basically are making a perfect correspondence between those. But now you need a plus sign. Other ways to get to N pesos. Besides going
You
to
can pay with
N-1
$5
pesos.
for $5.
If I have a $100 bill in my pocket, I don't have to go all the way to N-1 pesos. I can go to N-100 pesos and then pull out that bill. So it's gonna be kind of a long relationship. It's one of those things you kind of try. You'll just be able to write this one down. Let's see. When you have to.
There are 5. Oh, but we can check 2 ways.
that's, yeah. So when we start with it, we gotta like.
So we need.
So, 1 over 10. Give that to the cashier. And then you stay basically.
But
One peso.
Or you can start by doing that.
it's gonna be like, it's gonna be like, this is like.
And so on and so on.
That's like way back.
Right.
Because it's dead.
It's still. You can tell it's, keep it going.
Can you make $2?
How we doing?
Yeah, the last time the ministry does them in.
How many weeks?
No,
Okay.
so it-
It just gives a
That was
person.
the one away.
Oh,
I can make $5.
oh,
So, I guess-
There's only one.
Right
here.
You just have to.
Okay, you add 2 paper, then there's.
Cashier.
This is, you need to add $2 first. So how many ways to add? 5, yeah. $5 bills, 5 coins.
Five bill, 5 coins, or, so one case is I just want to get $10 out.
Yeah, and there's.
If I won, now the question is, well, you know what that's called, that's called.
So that's.
There, that's the one.
Right there. Or how many ways can you read
This is true, this is true, and you will.
Well,
see,
you are.
you
Yeah.
will get a
Yeah, like we should start with.
Terrible. Yeah, we did this.
So what I'm saying is, like,
Is that separate? If it's a coin, then it's. But we only did like 1 and 2. Sorry, 2s and 1s are multiple.
and then, okay, what if you didn't?
So we have to, we can make it.
No.
Yeah. 10.
And then.
Different ways are different ways.
When there's no overlap, because if I start with one peso.
You can do 5, 4, the 5.
So if we do this, we're gonna do it one for people, we're gonna do it. I'm not asking you to solve this.
It doesn't matter,
Right.
And the 5 ones. I don't think those ones will be hard science.
I was thinking the word battery. Write it down.
That would be. I.
There's two.
Is it like the
There's nothing saying or.
Is,
Basically, you're assuming that you have an endless supply. Let's
Yeah.
talk about it.
So would there
Endless supply of all money in the world, right? And you could just start.
So if we're talking about. I think the saying is that.
Okay. Anybody need a hand?
This feels like a Bill, yeah, Bill.
No, you're not having this line.
That makes it.
So there's this equals this plus minus one, so you're writing all out.
We're gonna find out how many ways you can pay for it. I've seen like we have to just think about it. And not just.
What is the first one, what is the first piece of money you're going to hand the cash out? Right? If you hand them the one piece of coin, then there will be this many ways for you to pay. The bills don't, if you hand them a paper.
Now, I'm gonna write it, like I'm assuming it's.
Right.
It's like.
And.
Maybe that's what we were thinking about.
Oh,
Like just 2 ways.
yeah, this is these coefficients.
That's
Right, so this is if you count some piece of coin, this is starting with 2 pesos. It's like 5 pesos.
Yeah.
There's ways.
I'm just saying like that. We were.
Yeah.
So.
That's a. Just write down. It would be fair. And then you have a 100-degree column.
Yeah, Oh. There's only one way to do it.
Yeah, but writing it down, it's actually pretty straight.
Right.
Okay.
I was glad to hear that. It's like a lot. There's gotta be something.
Yeah, it's looking really good. I like it. Well, I have a bunch of cases.
I'm like, oh.
So you have a 1 peso coin, or you have 2 pesos in the coin. But you have 2 5 peso items.
Oh, I think that's
Good. Add that. I love it. That's it. Yeah, that's all you have to do. Solving the relation would be horrendously bad, but at least writing it down is pretty easy. Okay, great. Okay, yes.
So there's
Yeah.
chunk at the end where it says if the order in which the coins and bills are paid matters. Are you saying like, so like we could make our 5 out of 221, 212, are you saying literally the order we hand them the coins matters? Or is it like this where you're saying you have a 5 coin, 5 bill, or 5?
No, I mean what you said first.
This-
The literally the order in which you have the.
Should we also be considering whether it's a bill or?
Yeah.
Okay.
Yes.
Okay.
So here's the thing. All I want you to do is think about which piece of money you hand the cashier first.
Otherwise, you start with one.
If it's a 1 peso coin,
Then you would.
then after you've done that, you have b sub n-1 ways to finish paying the rest of the bill.
The 101 was still doing math. I was like.
And you might use some 101 peso coins later or some other ones, doesn't matter. That's b sub n-1. The next possibility is maybe you started by handing them a 2 peso coin. Now, that would be different than handing them a one basis point, so this is a completely non-overlapping case, it has to be added separately, and that would be piece of it minus two.
Yes, you said five.
Me? Okay, so I'm saying, I'm making this choice, I'm going to hand the cashier the 2 days of the I've done that, I looked at my money, and say, how many ways are there for me to finish paying my money? And that would be the piece of n minus two, whatever that is. Keep going, so I agree with the piece of n minus one, I agree with the piece of n minus two. The piece of n minus five, I agree with that, however, with the piece of n minus five, I'd like to argue both for two. Because there's a bill and a coin, for both five. Right, because you could choose to do the 5 piece of bill first, or you could choose to do the 5 piece of coin. Those are two different ways of paying, because we're keeping track of the order. It says that the order that they were. Yes. So I don't know what the +1, +2, +6, that part of my. No,
Because our thought process was.
I mean, if anything, you should be both of them. Well, not even both. I think they just should be mine. Adding up a bunch of cases.
Yeah.
Yeah. Okay.
Erase right there.
Great. Let's see. It's coming along okay? Oh, I think. Yeah, okay.
How come it's not like one way to start?
Oh, wait. Yes.
Oh, yeah.
It is. It's a 100.
There are 24.
Well, and kind of is equal to 100, if you're wondering about that, then you have around here, like 0. And then, well, what is? Yeah.
Oh,
B0 is sort of like, I don't know. Like,
So
it's
minus.
all that one.
Minus one.
Yeah, so I would start. So.
The over in minus. Yeah.
That was equal to 100.
Right. So when you invoke more than one
At least 101, so that's.
you require yourself.
Yeah, you got to pay something.
It'd be, what?
It's.
When n is equal to 1, and then when n is, wait, we just need one, huh? We need. Then it says to do 2.
Oh, so then it's now.
Okay, hey, one second. 4, remember, 5. Yeah.
Oh, okay, yeah. Yeah, because in case we're putting like the one that's divided by. Yes.
I guess. Since I have these big plans,
Do you guys look at it? Yeah, I show it and someone, yeah.
Yeah.
Make sure
I like that.
Yeah.
But then it looks like you're taking to it, it's like starting from.
Yeah.
It feels very. I think it was probably say.
0.
Anybody need a hand?
0 plus.
0. Oh.
Plus 2.
Oh, L and minus.
Yeah.
I'm looking at it. Yeah, okay.
Oh, and then this is their.
I guess it wouldn't be much of a. We're just the same. Yeah, I guess you have.
0 plus.
So this is the reason I really wanted to come back to this problem was because it's similar to some of the homework that I did last week that people were writing down, like, this is great for like chicken scratch. Like, sort of figuring out how it works, but can you try to write it up nicely? So that means I wanna know what are the base cases.
But I wanted
And-
to.
Oh, you did that.
We were kind of.
Okay, yeah, so can erase that. And so my point is just, you know, by the time you're done with this, I don't want it to be like just all one. Trying to keep it nice or
No,
base case.
yeah.
Make it clear, you know, put some words on it. I'm assuming this, and I'm assuming this, and therefore I start with this, whatever, right? And just see if you can like, I think you have the right idea.
That's your-
Well written. I just want it to be well.
Oh, yeah, that's your.
What tree are we doing? Are we assuming it's minus one or are we?
One of the other players.
What do you think is gonna be easier? Sometimes the depends on what it's easier. I like that N, and minus one and putting N, because then you kind of get what you want. And then it's too hard to go to the others.
So you got one of them on the board.
You're saying
You're gonna see that it
mine.
might go down.
I think L like L two is, it's on these two and then. Okay, so you can let L two on some of these two.
Yeah, we want to show.
It's that we're trying to show them.
I get it, it's okay.
And then just copy.
Okay, so for the base
For
case,
all greater than,
So.
I think here we could say
Two.
for N.
And so.
Maybe it's for all N or for all N, here we would one and two strong and greater than or equal to three.
Well, we'll do left hand side, right hand side, right? And
Or we
then
could do like that, yeah.
Says anything, then we can.
Cause then, once you like sum up your induction, you could say for all N, equal to the one, two, and then you could then be greater than three. But,
So should we just? So.
so then start with, LX. Oh, yeah, you're gonna start with this, and then we can plug in this and this.
This is actually.
Yeah. They can say, yeah, just rewrite the Ln on the first side.
We're trying to this. Oh, yeah. I was just. It's like, oh.
And then by.
I was right now.
And then you.
Anybody need help?
With this. Because now you have Ln.
This looks great. Good job on that. Everything good, going smoothly?
I have a question. When we say that we want to show this, so we say for all N, greater than or equal to
It would be. Yes. That's actually this. Yes, for all and greater than or equal to.
And
Yes.
this one also by necessity, should we say it's for all?
Two
So we're actually.
FN plus one plus
Fif-
FN.
Oh, I see. We were actually
We have
fixing
FN
the
plus
value
two.
then.
Yeah.
So putting this, I see why this came up.
Yeah.
So it is true, you're proving this for all N, but while you're in the midst of doing induction, you're really focusing on like your assumption step and then the next version up. So it is as if you have fixed the N. So
Okay.
you're.
So we're just saying just that.
Just that this is true, and then you're just proving that this one is true.
Okay.
Okay.
Yeah, now I do think though, if you look at my hint, I did say that you are going to want to use both N minus one and N minus two versions. So you've written down the N minus one version,
But also.
but I'm guessing.
We assume both of them?
Is this an assumption? Oh, no.
No, that's already.
That's the reversal. But you can see you're gonna wanna plug in this.
Yeah.
So I think when you say we can assume this one, I think you can also right next to it, put down the N minus two.
Okay. Would that mean we need more base cases?
Two base cases,
Okay.
which is what, two
Okay.
base cases would be good enough for two, previous versions. Anybody need help?
That makes sense. Yeah, I realized that when I was doing this, I was like, I don't think I can put that in because we don't know.
Yeah.
How's everybody doing over here?
Good for 5 minutes.
Oh, nice, let's see, so we got, base cases. So we can, here's.
N minus two, and then N minus three, and then N minus four. So this one? Oh, I'm looking at the wrong one. Yeah.
I guess, but just, because that plus one plus one.
Yeah. I saw that.
There would just be one left answer.
Yeah, I would.
Yeah.
Yeah.
So assuming it's. Just start that, so it's like the end of six, and you go into the next.
Oh, I don't know what you guys.
Got this.
It's like the assume it holds for n. You can show
It was just saying this is.
Not just that, you need to use two previous versions of. If you look at your group here, you've got, like, you are
Right, because,
using,
but because the federal.
right here, you're using your assumption here. But you're also using, you're
Can we just say
using
that?
this box, but with
I
n
think
minus one where you have n. And
Yeah,
you say up to
I
some
can- I
n,
can
so I
actually
assume that
know.
means it's also true if you shift.
Oh, no, yeah, we've done that.
And so on. It's fine, I would prefer to see you explicitly writing the two previous assumptions.
Go on, and yeah.
Oh, instead of writing, I would just say, and L less than minus one.
Square to the both sides.
I would actually have both of them literally written down. And then this box is going in for this, and this box is going in for this. And then it just flows. The reason I'm having to work on this is just when I'm grading homeworks, the last assignment. This was in some cases.
I think that makes it harder, yeah.
Still, I mean, they weren't, it was.
So that's the-
Thanks for, to put it bluntly, there's a little messy, I'm just trying to have people work on polishing that. Right, and so.
Yeah.
So it's good when you can see how, what the assumptions are that are coming from your.
Because that's what we were.
Section step assumption and then using.
Should I? With us.
Okay.
Okay.
But it's totally the right. idea. Looks like.
I could just say we're done.
Yeah, I don't know.
Let's see. Assume that.
The last one is how to do. There's a B. A. Right. What time is it?
Totally good. And you did two.
Time to take. 5:52 B.
The movies. Did you get it?
Hi. Luckily, it's not that. That once you knock over the first.
And then the second one is B L0 squared plus L1 squared plus dot 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 plus LN squared plus LN plus 1 plus 2.
Where.
Well.
My favorite.
B is
L0 squared.
So you are.
L1 dot dot dot.
Well, these are the.
LN squared. Times.
Well, it's kind of going in reverse, it's saying I'm gonna.
I like how we're controlling Zoom. Oh, you were seeing, so they could see our next question. We want to prove that this is true. Using. How do we do that?
It'd be good to write down what it is you're trying.
I wonder which side would be easier to show the. Maybe the other one. Break it down into.
Anybody need a hand? You could.
Now we can maybe.
But would it be easier to substitute?
That's what I'm trying to say, like, which is the.
Easier.
Can we just substitute? I think.
I like.
I think we should start with this. I think so.
Wait a second.
Place your L0 and your L0 is 2.
Isn't this, this is the first part. So don't you need it back?
Oh, do we?
Is it better?
Can I make a suggestion though? So one of the reasons I'm asking you for these is just to clean up the right out.
Zero squared plus R
Let's
one,
kind of-
that's the first.
You start here, you go here, you go here. Yeah, so basically what I want is a white space.
And it was-
This could be just nothing really.
Yeah, look, zero.
Well, let's put it here.
Plus, and then one.
Yeah, cause it gets confusing, it's like, oh. That's just a term.
So that it would equal
You might think, oh, that's just a
4
but
plus
but
1.
actually, it's somebody's trying. Yeah. Don't be afraid to like write these out or like abstract it first.
Oh, yeah, we can.
Like, I'm talking about, just sort out the math and then try to polish it. That's looking good. That's good. I think you're gonna be able to. Great. Yeah, that looks great.
That looks great.
Everything okay here, guys?
Yeah.
You've really made this very, very neat, which is great. Well, you have good handwriting to begin with. And then on top. Well, organized, which is part of what I wanted to practice with this. So I'm really, really stoked about it. So you got your base cases going. Yeah. Sometimes I don't know. Cases I'm gonna need, and what'll happen is, when you go to the stuff and work on it, you just need to look in your work, how many of the previous versions are you using to prove the next version? And if you're only using the one version.
Go for C.
Go for a.
Two previous versions are good over there. You need to see these.
testing, trying to do that.
Exactly.
I mean, it's important, it's like, just proof something. It's like,
What's that?
the non-included.
Yeah. because
That's
it's
what you're
used
taking
to-
now?
It's just, Dr. C.
Oh.
It's just a lot of them.
He's usually taught the geometry class.
He
likes this class, but I've stolen it from him,
He
so.
does the screen.
Well, I think we
Yeah,
need
he does
the base,
all
we
of
need
it.
the base pieces.
I know.
So we have some experience with.
You have practice with that, yeah. Hey, guys, just so you know, it's, I know some people have an exam at 5:30. If you're good to go, feel free to check out for the day. Even if you're not quite done, it's okay. I can come around one more time and just make sure everybody's feeling pretty good about this. The key thing here, guys, is to try to clean up the Friday. So that it's not really-
B is like 2 times alpha. Alpha is 1. Yeah, which is 14.
Nice.
We know where we're going.
I can see.
From there, I feel like it's pretty standard, right? It's just like a
Yeah, it's not that big. We plug in other things.
Yeah, and it's like the question that we usually organize all section and how like.
It's just like, it's so much.
You got a picture?
It is once you study it. You have a class, the class is like, here's 10, you're gonna need to. And there's.
You're supposed to go back.
Yeah.
Later, guys. Bye. Good luck on your test. Take care. Add that to it, combine that, piece together that. Really, really nice. Great job, great job.
Yeah. And then they work out.
Hey, that worked out. Okay, so the thing here, I love, by the way, I love how this is done. You have your white space on this side. And you're just organizing the items. You know what?
Manipulate on both sides. I always just think, it gets confusing, like, well, what happened there? But if I've got it only going on one side, that is the call. Oh, here, here. I like it. Good job. Good job. All right. That's it for Tuesday. We're gonna start graph theory on Thursday. I can't wait. You like graph theory?
Yeah.
I do too.
I think you're gonna love, yeah, please bring your colors. You will find that to be